Hi there, I'm Hao. This is just another video of me solving random code problems. All paths from source to target. So given a directed mean one direction, right? Where directed mean one can get to two and two can get to one. But if this is directed, then only one can get to two, right? Acyclic graph, acyclic mean there's no cycle, right? So there's no infinite loop. So like normally when we iterate through the graph, right, we usually have a visited set to keep track of the node that we have visited to avoid getting into an infinite loop, right? But if it so like for example, we have 0, right, and 1 here, right? If we process node 0, right, and then we're gonna look at the neighbors of 0, which is 1 here, right? So when we look at 1, right, and we process 1, and we look at the neighbors of 1, which is 0 again, right? So we just keep going back and forth. So that's why we need a visited set. But if there's acyclic, which means we don't have to worry about that because we know for sure that there's no cycle. Okay. We have n nodes, right? From 0 to n minus 1. Find all possible paths from 0 to n minus 1 and return them in any order. Okay. Graph of I is a list of that you can visit from the node I. So this is an adjacency list, right? So 0, right, 1, 2, right? So node 0 can go to what? Like 1 and 2, right? Here, which is 1 and 2, right? So on and so forth. Yeah, so this is the first node, right? This is the last one, a minus 1. So we have index 0, 1, 2, right? 3. Wait, 0, 1, 2, 3. Yeah, okay. So we need to get to 3, right? We have 4 nodes. So one path is 0, 1, and then 3, right? This path, or 0, 2, and 3, right? Which is this path. So this is what we have in the result. So um, because we are finding all possible paths, right, from a node to a node, so it doesn't matter if you breadth first search or depth first search, right? So I'm just gonna use depth first search here. Right? So okay, let's create some variable. So just say n is equal to graph of length, right? We have the result to store our path. We return the result at the end, right? And we're gonna do our DFS of 0, which is we always start from node 0, right? With and then the path will be 0, right? Because we start from node 0, so the path will start at 0. And we just have to create our DFS function here, which is our node and path, right? Okay, so what is our base case here? So if node is equal to n minus 1, we want to push the result, right? Push the path into the result and return. Okay. Yeah, there's nothing too crazy with the constraint here. You know, the element will be unique. Okay, that's good. Okay, so if we reach the node n minus 1, right, which we will return the results. We will return after we push the path into our result array, right? So that is one path, and then we just keep going, right? So what do? We want to look at the neighbors, right? Which is the graph of a node here, but for each right neighbor, then we're gonna do the EFS of the neighbor, right? And then the path, right? Dot contrast the current node, right? No, the concat the neighbors, right? Not the node, because the node is already in the path, right? The node is already in the path here. So if it is not the target yet, right, we just keep iterating. Neighbors, right, and we just adding the neighbors to the path, right, and just keep going. And I think that's it. Give it a try here. Okay, submit. And thank you for watching.